My first lecture is I want to prove to you that SolidCAM is on the right way. And who is better than SimData to tell us what's happening in the market? What do we need in CAM? So, according to SimData, there is a growing need for more sophisticated CAM. You could read it in the latest report. Okay, why there is a growing need for more sophisticated CAM? Because manufacturers are striving to produce higher quality goods that could command higher prices and yield better margins. Every manufacturer, that's his target, to make higher quality goods and get better margins. Now, higher margin performance derived from producing higher quality goods and lower labor and lifestyle costs remains the strongest driver today that pushes the adoption of sophisticated CAM software. That's what I'm saying. People need more sophisticated CAM software, and we have to provide it, obviously. So, higher quality and greater margins means manufacturers need them to produce higher quality goods. Now, these highly finished goods generally require sophisticated engineering and machining that in turn require sophisticated CAD/CAM software for design and manufacturing. Another problem today is the scarcity of experienced engineering and machining personnel in most developed economies. And this is driving the need to capture knowledge and automate as much of the machining process as possible using CAM software. This is what we are saying. People want more advanced CAM software, also want automation, because they believe that you need to capture the knowledge of the more experienced machinists and use it for those who are less experienced. Okay, so from the technology side, what is this growing need for more sophisticated CAM? What does it include? First, because of the continued increase in the use of multitasking machine tools. They are becoming more and more because they are much more productive. Also, there is a growing demand for physics-based cutter path strategies. I will explain later what do you mean physics-based cutter path strategies. Also, product design and manufacturing must respond to the trend toward more aesthetic designs. Everything now designed and becoming more aesthetic, more good-looking. Once cars were boxes, now they are so well-styled. So we need better design and better manufacturing. Another important driver is there is now creative use of additive manufacturing. And that's why the reason why 2 years ago we decided also to go into this additive area. So the market will place a premium on the products of software solution providers who develop and deliver a superior response to these drivers. And that's what we are trying to do. Okay, first let's talk about complex machine tools. Machine tool complexity and capabilities continue to increase, driving the need for sophisticated CAD/CAM software to create the NC programs required to synchronize their complex capabilities and to optimize their usage. Anybody who uses a Swiss machine understands how important this is. So the introduction, acceptance, and support of multitask CNC machine tools is a dominant trend in the industry. I believe in the next couple of years, every machine shop, if they want to be productive and make money, they need to have more sophisticated and advanced machines because they are more productive, so they could win more jobs compared to others. Performing multiple operations such as milling and turning on a single CNC machine tool, and often in a single setup, typically results, as I said, in increased productivity, faster turnaround, reduced scrap, and improved part quality by avoiding errors in transferring components from one machine to another. I was visiting one of our customers in India who was doing medical parts, and he had many mill and turn machine, regular machine, and he had a Swiss machine. And he told me that once he got the Swiss machine, before he had to do a medical part, he had to move it to 6 different setups in different machines. And now he could finish the part with one Swiss machine. And since the Swiss machine works automatically with the bar feeder 24/7, it became a money-generating machine for him. It's amazing what these Swiss machines can do today if you know how to use them for the right type of part. Not every part you can do it on a Swiss machine. Usually smaller parts, but complex, like medical parts, also electronic parts, you can do them on Swiss machines. Okay. While more capable, these machine tools are becoming increasingly complex to program and use. So you need specialized software to effectively use these multitask machines. The software defines the tool movement, simulates the operation. Simulation is very important, and post-processes the output. Simulating movement is extremely important for an operator to visualize the machining sequences, avoid collisions, and optimize the operations. I think anybody not working with CAM software, just trying to finger CAM on the Swiss controller, he doesn't see any simulation. To test his program is really a very difficult process if he doesn't have simulation. CAM software must provide individual control of each turret synchronization, and produce accurate cycle time calculations. Sync and wait marks must be added to obtain the desired concurrent operation. Obviously, these all sync and wait marks are generated automatically using our operation sequence manager. By the way, they are not talking about SolidCAM, but they are talking in general. But as you see, as I mentioned everything, this is what SolidCAM is today. To program the multi-spindle, multi-tool capabilities of a multitask machine, it is common for the cutter parts to be programmed in the CAM system independently. They are then synchronized automatically by the CAM system, manually by the programmer, or combination of both. Here I want to explain something. Today, somebody who has even a simple CAM system like MasterCAM can generate a tool path for each of the different operations, I mean the different turrets operations. And then he could go get the code for all the different channels, and then on the machine try to do this synchronizing right on the controller. This is not the right way, because it doesn't have simulation, because he generated the tool path for each channel separately, and then he is doing the synchronization between them right with G-code on the CNC controller. This is not the right way. He has no simulation, and it's a lot of work. While in SolidCAM, this is done by our operation sequence manager. Okay, when executed on the shop floor, the machining begins with the sync codes orchestrating the program flow for each execution channel. ANSI programmers can verify the ANSI programs and their sync codes before using them on the shop floor. It's very important, this simulation. That's the advantage of having a CAM system rather than doing it on the controller. If balancing the execution of the individual channels is necessary, it may be required to edit the sync codes. This also can be done by somebody who's an advanced user. So the growing use of multitask machine will continue to drive demand in CAM functionality to support their ever-growing levels of flexibility and complexity. Okay, so you are convinced SolidCAM can do that, whatever they are saying here? Okay, next. People want physics-based cutter path strategies. What's meant by that? They want the tool motion to be dictated by physics-based analysis. I think Kev Merritt can explain it the best, but I will try just to say it in general. Okay, these physics-based strategies are designed to produce highly effective and efficient tool paths, significantly reducing machining cycle time, that's a big advantage of iMachining, extending tool life, and improving part quality. Most of these physics-based strategies excel when machining hard materials. Isn't that iMachining? Titanium, when you cut harder material, we save even more I think they were talking about solid CAM, but they said in general, this seemed that. Okay, most traditional cutter path motion strategies are based on the strict geometric shape of the area to be machined. You know, the regular pocket, what was done, take the geometry and do offsets. This is what they mean, that traditional strategies are based on strict geometric shape, plus one or more other geometric properties like step over, for example. Physics-based cutter path motion strategies are based on the way a cutting tool progresses through the material. I think Doron Soplansky, our CTO who wrote iMachining, can explain to you better what it means when you progress through the material, how you create the tool path. Okay. The step-by-step definition of tool motion considers the area from which metal is to be removed and how the material being cut changes throughout the various machining stages. The resultant motion evolves by looking ahead to see what is coming up and modify feed, step over, and cutting motion in response to the ever-changing material conditions during part machining. That's iMachining changes the feed all the time. Every point of the tool path can have different type of feed. The software solution relies on physics-based assessments, such as ensuring constant mechanical lateral force on the tool. That's what I said always. iMachining ensures constant force on the cutting tool and spindle, or managing the volume of material encountered and removed with each movement. Another criterion that may be employed to determine tool motion speed and feed is to assure the heat generated in the primary shear zone, the contact area between the moving, rotating tool and the part, is mostly carried away in the chip. This is iMachining. All the heat is carried away through those chips that come out with iMachining, minimizing the amount of heat conducted into the workpiece. So when you touch the tool after you cut with iMachining, it's not hot, right? Really, they are just saying iMachining. So these criteria usually result in tool paths that maximize tool in the cut time, no air cutting, minimize wasted motion, air cutting, reduce jumping around in pockets, you know, iMachining, there's no jumping around, and smoother running of the machine. Typically, they possess continuous tangent motion. That's iMachining, tangent all the time. A more consistent tool load rather than sharp interrupted movements. Okay, so, you know, they say this is the trend of the future. We already have it in solid CAM iMachining. Next, as I said, because products are becoming more and more nicer, you need more aesthetic product design. So you need then, with these complex shapes in an aesthetic design, these shapes need for CAD/CAM software that can model complex shapes and create sophisticated, efficient NC programs. Use of analytics to create more optimal part geometry is also producing non-standard shapes, requiring more sophisticated CAM programming and machine tools. Here comes additive. Additive manufacturing plays an important role because it's possible to generative design. Today there's many generative design programs that generate all these shapes, where you tell it, I want to have these forces, this is the area, and they produce a shape for you. There are many programs like this. But these shapes usually, it's very difficult to CNC machine them. You have to 3D print them and make them finish with CNC machining. So the generative design techniques create shapes that could not be manufactured using conventional subtractive machining. Or it will be too costly to make them only with subtractive. So the improvement in additive manufacturing techniques is having a growing impact on the CAM market. 3D printing offers an increase in the complexity of product designs, as I said, which increases demand for more sophisticated subtractive CAM. Through generative design techniques, as I said, there are programs that do that, we create shapes that could not be made using conventional subtractive machining or are too costly to make. I mentioned this already. 3D printing and subtractive CAM are often used in a complementary fashion, with 3D printed components forming a base that requires subsequent CAM operations that can be used to create threads, for example, remove support material, break movable parts free from the surrounding matrix, or create a required surface finish. This we have seen it a lot. Demand will increase for CAM systems that can program hybrid machines that combine additive and subtractive in the same machine. And this is, for example, today, there is a company in Spain called Melchior. They create a laser head with a controller for it, and it could be combined with any CNC machine. So I've seen it with Haas. Also, I've seen it also combined with other Spanish CNC machines. In this combination, you could 3D print and then do CNC machining for finish. Or less usually the opposite. First, do CNC machining and then do 3D printing for some things that protrude from the part. But mostly it's used to first do 3D printing and then CNC machining. For example, when I was in IMTS, I met somebody who is supplying this equipment to Navy ships. Because in the Navy ship, usually they need spare parts, and they don't carry all the spare parts of a complete Navy ship. So what they usually do, they use a Haas with a Melchior head, and they first 3D print the spare part shape, and then they do CNC finish. Why they first 3D print? Because usually the Navy ship doesn't carry too much stock material. So the wire used for the laser head is enough. They have wire, and with this wire, they could generate any shape with 3D printing and then do CNC machining. So SolidCAM 2025 will be the first system that could drive such a combination. Let's see here some examples. Usually in hybrid machining, we have different types of operations, like area laser-aided operation, multi-layer laser-aided operation, tool laser-aided operation. These are different types of laser printing. Here we see a complete simulation of a tube spine machine simulation. Okay, Jack, let's see the simulation. This is working inside SolidCAM 2025. So the part was first CNC machine, and now we are adding this tube by laser printing. Okay, you get the idea. Let's move to the next slide. So this is the result. After you finish the 3D printing of the tube spine, this is the result. Alex Myasnikov is the manager of this, product manager for this project. If you want to get more information about it, you could talk to him. We'll be releasing it in SolidCAM 2025. Thank you.